Hi everyone, in this video I want to show you how to apply curve fitting with the help of SplineCloud. So this is going to be a basic video, really a basic use case study for SplineCloud, and what I want to do is compare how to apply curve fitting with and without the help of SplineCloud. For this comparison I'm going to use Python and its existing numerical libraries NumPy and SciPy that provide a whole range of tools for curve fitting. Now, if you're already using Python, you're probably familiar with these libraries, and chances you have already done some curve fitting with NumPy and SciPy. And if not, well, you can definitely learn how to do this from this video as well. So in this example, I decided to use something interesting, the efficiency of a propeller as a function of the flow velocity. You see, if we go into the theory of propellers and dive deep into that, we would discover that each propeller has this peak of efficiency at a specific velocity of flow. So what we can do is go to the website of APC propellers, and they have actually provided lots of data for the simulation of their propellers. From that data, we can learn exactly how each propeller behaves at different velocities and find out where it performs best. So for our comparison today, as I mentioned, I'm going to use two approaches. The traditional approach with NumPy and SciPy, and we'll use Jupyter Notebook for that, and then the alternative approach using SplineCloud. So let's go to the data itself. If we Google for propeller performance test data, APC website goes to the top, and as I said, they provide lots of data files with the simulation results for each propeller. So we can just go and grab this one, 14 by 10. So the data file structure goes like this. Basically in the header you have some information about the parameters that are described here in data. And then you have those tables with different parameters for each RPM. So this goes for 2000 RPMs, 3000 RPMs, and so on. So let's pick one of them. Let's say I want to go with this one, 6000 RPM. We will just copy that and create a table for that. I will remove the second line, the second header line, just to avoid some complexities in data loading. So let's save this file. Okay, 6000 RPMs. Here we go. And now we go to our example, to notebook example. Basically what we do here is, first of all, we load NumPy, we load some libraries from SciPy. From SciPy interpolate module we load interp1d, which is the method for finding the interpolation function. And from SciPy optimize we will load the minimize method just to find the minimum of the function, to find the optimum with the help of this minimize function. And we will load matplotlib to show the results. So let's go. And we will change now this data file and this data loading function to 6000 RPMs. We can now check the data. Yeah, so data was loaded successfully. So now what we have to do is we have to extract the columns that are of our interest and apply curve fitting for those columns. So if we go back to this data file, we can see that column with index 0 is velocity, and column with index 2 is propeller efficiency, the one that we are interested in. So let's go back to our notebook. So this is what we have here, the first and third column, right? Let's go. All right, so basically now we have interp function, which was constructed with the help of this interp1d, which is the function that interpolates our values of data points. So to show the results, we will evaluate this function for the range from 0 to, let me check, what is the maximum value? 71 here. Okay, let's go to 71. 71 miles per hour is the maximum value in the simulation data. Okay, so this is our curve. And if you take a look at the interpolation function, there are specific commands here. Kind linear, which means we apply linear interpolation, and fill value extrapolate means that in the range beyond the values in the data, we will extrapolate values, which is useful to avoid some non-values when we plot it or when we do optimization. So we can evaluate it for some velocity, say 10, and the value goes 0.27 miles per hour, something like that. So we see that this function, interpolated function, behaves as a function. So now we can find optimum of that. Optimum would be the maximum value of efficiency. So this should be something like 55 or maybe 54 miles per hour based on the plot. And what we do is we construct the objective function as a reverse of our function and apply minimization. So this is basically very simple. Okay, 53.9. So yeah, as I said, 54 miles per hour is the maximum efficiency at this velocity. Okay, so going back to our presentation, what we have learned from this method. So basically, what we need is always we need the data file to be allocated with our code. So if we want to share our notebook or maybe our code with somebody, we have to be aware that we also have to share the data file, and it has to be in the same folder, or maybe just a path should be tweaked for data to be loaded. So data files have to be there. And each time that we rerun our code, SciPy goes and finds the fit again and again. So imagine you have lots of data files, lots of data, and it will take time and resources each time you run the code to find the fit. And smoothness. In our case, we used linear fitting. Of course, SplineCloud provides you with lots of different values, different methods for fitting with splines, with different kernels, not non-linear kernels. But smoothness is something that you usually have to consider if your data should be smooth, right? And fitting methods are hard tunable. What do I mean by that? If we go to the documentation of SciPy, we can take a look at those interpolation methods, quite a few of them here. And if we just pick one, maybe I'll just go cubic spline, for example. So those are different parameters that we have to pass. And for each method, we have to know about different parameters. So tuning curves, selecting the right shape is tedious. It takes time. It takes you some effort to find the best curve for your data, which can be exhaustive, especially if you have some complex data. So what is the alternative? The alternative is to use SplineCloud. So let me go back to my presentation. Let me just go back straight to the notebook with the example of fine-tuning with SplineCloud. So in the case of SplineCloud, the approach will be different. So let me just go to SplineCloud platform, sign in. Okay, so in the case of SplineCloud, we have to create a repository on the cloud. I already have this test prop data repository, so probably I will just reuse this existing repository, not to create another one. And we will upload data here, not in the code, but on the cloud. So now we have just to click on that file, and the dataset is automatically created for this data file. So we have some options for loading data. We're currently working on improvements here, so you will have more options soon. But basically, as you see, the table like that loads perfectly with no hassle. And now what we have to do is click click fit curve and select the response variable. So in our case it's propeller efficiency, and just click add curve. So it automatically fits. By default, SplineCloud provides you with smoothing splines, which are approximating splines. They don't pass through each data point. And for our case, we want to use interpolating splines because we will be comparing results with interpolation method. But in most cases, approximation is what you need, especially when you have big data files, lots of data there. You don't want to bother with interpolation and consider fitting every single data point. You want something smooth that goes and approximates and denoise your data. But anyway, in this case, we use interpolating splines. And what we have to do right now is copy this ID. We have this button, copy ID of this curve. We go to our notebook, and to reuse this curve, we have to load SplineCloud SciPy library. It's called that because it's using SciPy. It's based on SciPy. And what happens here is that we import this library. You can install it from pip install SplineCloud SciPy, which is quite simple. And this library, client library of SplineCloud, provides you with load spline method. There is another one, load subset, which loads data, but here we load a spline, and we will replace the ID of the curve to load our curve of particular interest here, and we will re-evaluate this curve for the range 71 maximum value of our data range. So here we go. We just pulled the curve from cloud into our code, and now we can evaluate it. So it's not a function, it's method, but it has its own its object, and it has its own method eval. So now we can evaluate the spline, and as you can see, the result is very close to what we have with interpolating function that we constructed with the help of SciPy. So now we can find optimum just in the same manner, but we have to consider that the spline is not a function now, but object, and we will call the eval method inside our objective function. The strategy is just the same. So okay, now we have 52.9, so a little bit different, right? So here we had 53. The difference goes because of the different shapes of the function. So here we had linear interpolation, and in the case of SplineCloud we have spline interpolation, which is smooth. So this can explain the difference in the value. Of course, you can use another shape, another curve for your data. All right, so what are the benefits of using SplineCloud? Those are obvious. Your data is now hosted on SplineCloud. You don't have to worry that your data file should be attached to your code, so you can share your notebook or your code with your buddy, and you don't have to worry that you missed the data file to attach the data file. So refitting now is not an issue, because on each run of the code there is no refitting. Curve was already fitted and hosted on SplineCloud, and on each run you just have the code just goes to SplineCloud through API, takes data to reconstruct the curve and reconstructs it in the code. So smoothness is inherent to all splines. So you can go down to the order of 1 and you will have linear interpolation just in the same manner. Probably I had to do that to compare, but anyway. By default you would have the order of 3, which provide you with smooth splines. And SplineCloud provides you with 3 methods: interpolating splines, smoothing splines, and least square splines. So you have 3 strategies that you can use to find best fit. In most cases, those are more than enough to find best fit to your data. But in case of some complex data, some complex behavior in your data, you have ability to fine-tune the curve. What do I mean by that? Let's go back to SplineCloud. We change type to smoothing, and now we have option to fine-tune. We click on fine-tuning, and we can drag those control points to fine-tune and find the better fit for our data manually. And to understand what have changed, we have this fit accuracy here. So it had to be improved. Let me just reset curve. Right, so we had 7, and after fine-tuning we obtained 4. So this is the option that you have as an advanced option that SplineCloud provides you with, the fine-tuning. And this is quite helpful when you have complex data. So be aware of this method and just go and try that. So those are benefits of using SplineCloud. And this is it for this video. I just encourage you to go sign up on SplineCloud and try this on your own. And thank you for your attention. Subscribe to SplineCloud channel for new updates, for new videos, which will come soon. And leave comments under this video. I'm interested in your opinion, in your feedback. Thank you.